Hi, today's tutorial is going to be on geometric operations for geoprocessing. So geometry is a branch of mathematics that deals with shapes, sizes, properties, and relationships of space. So an example of a relationship of space is that, for example, two shapes can be overlapping. That's a relationship. It provides a foundation for understanding the physical world and its structures, as, for example, to create a representation model of geospatial data, as for example, the size of a field or maybe a country boundary. So, the most basic concept in geometry is a point with no size or shape, and it can be represented with a dot. Geometric shapes can be created using these points, can also be used with lines, circles, and curves. So, for example, our circle over here, it's easy to represent with a curve. So, with an equation that can define its boundaries, not as easy if you want to use only points. But that's what you need to do if you are working with a polygon. So a polygon is a closed geometrical shape with a straight line. So it's already discrete. We are not using equations now. We are only going to use points. That's what we use, for example, for GIS applications, and everything that needs to be on a computer needs to be discrete. It is defined by its vertices that are points where the sides met, and then the edges that are line segments that connect those vertices. So polygons are usually saved as a set of coordinates defining those vertices. They are points. Operations between different polygons are possible and may generate one or more new polygons. It can also be empty. For example, intersection of two circles that do not overlap, that's empty. In our example over here on the right, we got two shapes, A and B, A blue, B yellow. If we calculate the difference between those two, the order matters here. So the difference of A and B, it's only going to give us A minus the B. And then if the order is swapped, then we got B minus A. If we got the union of these two, then it's just both of these shapes merged together. If it is the intersection, we only got the polygon where both shapes merge. And then if it is the symmetrical difference, it's just the exact opposite of the intersection. So on today's tutorial, we are going to use polygons. These polygons are going to be used for mapping purposes to represent geospatial data. Into the applications, they can be defined by points with the latitude and the longitude, and then can be saved with several formats, KML, GeoJSON, shapefile, and there are several others. So usually the first and last point are going to be the same. This is in order for us to represent a closed polygon. I'm going to show you two tutorials. The first one, it's going to be a little bit more simple. We are going to analyze how to represent a polygon on Julia, do geometrical calculations with those polygons, then Boolean operations between polygons, geometrical set operations between polygons. On our second tutorial, we are going to read the GeoJSON from the internet. We are also going to write one on a file, open a country shoreline, and then generate the area around it that limits its territorial sea, plot that area, and then use it to determine if a point is or not inside the calculated area. So on Visual Studio Code, we are going to create two different files here, tutorial 1 and tutorial 2. The first tutorial is going to be the basics. So I'm just going to show you guys how to do some easy operations with the functions available on LibGEOS. And then the second one is going to be a practical example, and it's going to be a little bit more advanced. Let's call it like that. So for our first example, it's going to be something simple. I just want to show you the functions that we got available. And it starts with points. I can just go over here and call the function point in order for me to create a point. It's as simple as that. And I want to create a second one, not centered on the origin, but with an offset on the x-axis. So P1 and P2, perfect. We can go over here and plot those two. In order for us to use the same plot, I can use the exclamation mark. Okay, and here we got both points, the blue one and the red one. As you can see, it works pretty well with the plots library, our LibGEOS. And it works not only with points, but also polygons. For polygons, I'm going to define some circles over here based on our points. So I'm going to use the function buffer. Buffer, what's going to allow me to do is going to create a circle around my points, but it could be also a polygon. Okay, this buffer is very generic. And I'm going to do for both P1 and P2. Let me see if I plot correctly this time. So C1, C2. Okay, and as you can see, the order of appearance is based on which one is plotted first. So if you plot C1 first, it's going to appear below, but you can also change the order. And if you want, for example, C1 to appear on top, you can just do it like this. Okay, so plots also work. We can do geometrical calculations with these polygons. So I can calculate the centroid of C2. It's pretty easy. I already defined that it's actually P2. So 1 and 0. And I can also calculate the area of a polygon. And hopefully you are seeing from this value something similar to pi. Okay, why is not actually pi? Why the area of the circle with a radius of 1 is not pi? That's because of the number of points that I'm using to define my circle. It's not enough. I can increase, and the function buffer allows me to do that. And if I do it, I can define it here, the number of points per quadrant. And if you guys are interested, I can show you the number of points of the polygon. No, it's get size, and I actually need to use the pointer, not the variable. I think it's like this. That's it. Okay, so it's 401. So 100 points per quadrant multiplied by 4 quadrants of the circle. And then you also add the last point, because the last point needs to be the same as the first one in order for us to know that the polygon is closed. And that's why we got 401. The area should be now pretty close to pi. That's it. 3.14, and then there is not exactly the same algorithms, but it's now getting closer. So the area. Now, Boolean operations. We can do a lot here. Intersects. Okay, so this function allows me to know if a polygon intersects the other. It doesn't show where, but only if. So in this case, both polygons intersect, and we can use the same function not with polygons, but with a mix of polygons and points. So in this case, the point 1, that is the central point of circle 1, does not intersect C2. Geometrical set operations. So imagine that you actually want to know where these two circles intersect. For that, we can use LibGEOS intersection between C1 and C2, and we can see where they intersect. This is not the only geometrical set operation function that we got available. We can also, for example, plot the union of both shapes, so C1 and C2. And we can see here that we got our union. It would actually make sense for us to do with the order like this. So you can see both the union and the intersection. Well, yeah, looks way better this way. Okay, so union, intersection, and we can also plot the difference. This is actually a pretty important function from the library. So difference between one and the other. So you got here this moon shape over here. But it's important for you to know that the function takes in consideration the order of the variable. So we are removing the intersection from circle 1, but if we want to remove the intersection from circle 2, we just change the order of the variables, and it works like this. So these are the basic functions from the library. Hopefully this gives you the basis. And now what we are going to do is create a practical example on tutorial 2 over here. So let's do that. So on this second tutorial, we are going to use a couple of libraries. We are still going to use LibGEOS, then Geodesy, that is going to be used to convert between latitude and longitude to UTM in order for us to do some calculations. GeoInterface to create the interface between a couple of packages here. I'll show you later. Plots, we're still going to use this for debugging actually. Then HTTP in order for us to download some GeoJSON files from the internet. And then ArchGDAL for us to import those GeoJSONs and also export again. What we are going to do here is going to be first, we are going to get a country map. And then from that map, we are going to calculate the national waters around that country. For that, I'm going to download from HTTP get our GeoJSON file. So by the way, the website that I'm using is cartographyvectors.com. And from those vectors, I'm going to use Madagascar as an example. So let me show you the website first. This is it, cartographyvectors.com. You can go over here and you can even download KML, GeoJSON, other types of files here. But I'm just going to show you guys, as I'm using GeoJSON, it makes sense for us to actually download it directly from our application. But this is the source of that map. So we can already go and run it. Okay, so we downloaded. You can see already here a couple of coordinates. But what we actually need now is to deal with these coordinates and put it on a vector. So for that, I'm going to use ArchGDAL, and I'm going to read this string that is the body of the HTTP response. Okay, perfect. Now I got this GeoJSON file. This file, you are going to see that there is layers here. So you can see that the number of feature layers is actually 1. And for that, I actually need to extract that layer from the file. I use the function getLayer. And here we got it. There is tons of information here. You got the geometry, that is the one that we are interested in. So we got polygons, but actually multi-polygons. This means that we got more than a single polygon. That's because the map that I'm using from Madagascar not only has the main part of the country, the biggest island, but there is also some smaller islands that are part of this multi-polygon. Then this variable is actually an iterator, so I need to pick up the first one of it. For that, I use the function iterate, layer 1, and I pick up this value. And I'm going to actually now get the part that I'm interested in, that is actually the geometry itself. For that, ArchGDAL, and get geometry. Okay. Perfect, from layer 2. Now, I should have on my variable only the geometry here, that is our multi-polygon. From that geometry, I now can extract the coordinates. I'm going to use now this GeoInterface library that I was talking about earlier, and I'm going to get the coordinates for G1. Perfect. Now I do have the coordinates. You can see here that the type it's it's vector, 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 vector of float 64. So it's a kind of a complex type over here. We don't need all of this information, of course, and we are going to simplify that. Yeah, but what we have then is this variable over here. So let's push further. And we are going now to start with the perimeter around each land mass. So as I've told you before, this continent has a couple of islands. So we need to generate a perimeter around each one individually. So for that, we are going to start with an empty polygon. I'm going to create these two variables over here. I'm going to start with my loop. So for all our coordinates, and we can give it a quick look to see how much is that. So it's 3. What we actually got is our main island and then another 2 smaller ones. Okay. And first, if we are going to need to do operations on these polygons, we need to convert those from latitude and longitude to UTM first. So convert polygon to UTM and then calculate the perimeter around each point of the polygon. Okay. So the first thing that I'm going to get is going to get the coordinates for each of these islands. And it's a vector of a vector of a vector. I can reduce this. You can see it's 3 islands. And I need to reduce it to, well, to be only a single vector. I can do it. I need first to collect for all of my islands the coordinates. So I'm currently working with island K1 over here. Let me quickly debug it just to see if all is okay. Did it work? Yeah, it's still a vector of a vector. Okay, so poly2 horizontal concatenation of poly1. Of course, no issues. I run it over here. Okay, and now I do have a matrix of these 1566 points, and each point, of course, with the latitude and the longitude. Perfect. This is something that I can work with right now. I'm going to create a polygon with this. Okay, perfect. Now, what I have now is this for loop that iterates all of these functions for all of our islands, but now what I need to work with is actually UTM coordinates. So I need to change from latitude and longitude to UTM. I'm not going to lie, it's going to be slightly complex here. Poly2. And if you guys have checked out the previous tutorial on GIS, you know that this function works in reverse order. So I need to swap latitude and longitude over here. Okay. Now I pick up latitude and longitude, 3 dimensions. I need to convert it to UTM now. TMZ from latitude and longitude for WGS 84 for my poly LLA. Let's give it a look. See if I didn't commit any mistakes here. Okay, looking good. Was converted from latitude and longitude to UTM. That's good. Now, next, I'm going to extract all of these data to points. And then from those points, I'm going to create, well, a circle with a central point on those points of the polygon. I'm going to still use the same buffer function that I was working with before. This part can be a little bit more troublesome. That's the conversion between latitude and longitude to UTM. I do understand that this can be a little bit troublesome. Maybe in the future we can work on a library that does this for us. So get field for X and Y. Okay. And now I'm going to use the function that I was talking about, the buffer one, in order for me to create a circle for each point of the polygon. Now, what's going to be the size of the circle? If we go, actually, we can give it a look at territorial waters. So we are interested in a territorial sea, that is a belt of coastal waters, and it's usually 12 nautical miles or 22 kilometers. Perfect. I'm going to use the 22 kilometers. And now we should have our vector of points that it's now going to be translated to points UTM is not defined. Points UTM, of course. That is going to be now converted to a vector of polygons. Is it? Perfect. Vector of polygon. So which polygon is a circle? And this vector has a circle for each individual point of the polygon of a single island, a single K1 island. Okay. Now I'm going to convert back all of these circles. Convert each circle poly back to latitude and longitude, and I'm going to merge them. In order for us to merge them, we are going to use the same function as before, as on the tutorial 1. Maybe I can show you again our union over here. Okay, but first, let's create an empty polygon. I'm going to create another for loop. Oh yeah, so I need the coordinates first. Once again from Geo interface. Coordinates, perimeter, K2. Then I need to concatenate this first. I can show you step by step over here. So let's give as an example K2. Okay. And then you can see that if I run the coordinates, I still have a vector of a vector of a vector. That's fine. Let's concatenate this with hcat and p1 of 1. Let me check if this is enough. It is. We already have our matrix over here. Perfect. And from that matrix, we can now use once again our Geodesy package. save these points as our type UTM-Z. Also requires for us to give the zone, the UTM zone of each point. And if it is or not north. Okay, it's now on the UTM-Z format. I'm going to use a transformer from latitude and longitude to UTM-Z. And let's transform these coordinates. Okay, looking good. We now have latitude and longitude. And as we have these coordinates, we can now create a polygon on LibGEOS, and we can do all of those operations that I've shown you before. In our specific condition, we only want the union one with LibGEOS. For that, I need to convert then this to a format that I can import with LibGEOS polygon. Get fields. For longitude, and then get field for latitude. Okay, we now have a matrix that we will use to create our polygon. And we have now converted in this format or of vector of float64. That is the one that our LibGEOS polygon is expecting. And we can go on and now create our polygon. We actually need another vector here, but I can just use the square brackets for that. Polygon. Okay, it converts. And now we can just use our union, a function from LibGEOS, in order for us to join together all of our circles that were created. Coverage for each point of our polygon. Of course, we are inside of a for loop, so I'm going to use this variable coverage here to save the data each time that we iterate this K2 variable over here. Now, the first time that we do it, there is no issue because we are using the union with an empty polygon with actually one polygon that is a circle. So this is going to create our first circle. The other ones is just joining together circles and putting those on the variable coverage. We can now save this coverage over here. And we can actually plot it. Yeah, why not? Just for you guys to give it a look. I'm going to run here for a single island. So let's run it. That is a lot of points, so it takes a while. And we can go on and plot the coverage. I cannot run it here because we have a not closed for loop. But I can plot here on the right. And as you can see, there you go. It does look like Madagascar over here. Okay, but with all of these circles from the points that we have gathered from the GeoJSON file. Okay, So it is working, at least for this first island. And then after we have this first island, we can store it on our full land and full coverage in the same way that we have done before. That is, these variables are empty over here that I've created before. And we can just put the polygons over here with a union. So here it's full land, and I'm going to put on a full land our polygeos. This saves the coastline, and then the coverage is going to save our national waters over here. That is our full coverage. It's going to be unit with the coverage. Okay, looking good. So yeah, I now have all of this full land and full coverage here. So if I run everything now, I should have these two variables with the country boundary and then the full coverage with our territorial waters. So hopefully this will work. Okay, this is the full land. So you can see here a couple of islands. So I guess at least these two over here. And if we plot the coverage, we'll see the national waters. Yeah, so what would make sense is that you'll see that the national waters are being calculated from the shoreline of the country, and it can either be inside of the country or actually on the water. So if I plot it like this, it's going to be more visible. So plot full land and plot our full coverage. And you can see that it's actually inside. If I actually now change the order, I only need to plot the land again on top. This would actually be the one that makes more sense over here. That is, in green, we got actually the country itself and the land mass. And then what I actually want here, it's our coastline plus those 22 kilometers that I put there before. So actually what I want, it's to subtract our full coverage with the full land. There is actually a function as well on LibGEOS that we can use to do that. So calculate the national water boundary and output to a file. So this will be only the water itself, so water coverage. It's going to be calculated by using our function difference, the same function that I've shown you before on tutorial 1. And I'm going to subtract now the other matters here on the function. So I need to do first the water coverage, then the land, because I want to retain with only the water part of our full coverage. Full land. Okay, it is calculated. We can go ahead and try to plot it. Water coverage. Okay, perfect. Exactly what we wanted. You can see here the shoreline of the country, and then on blue, the national waters with those 22 kilometers of distance from the shoreline. Perfect. We can actually now also export this multi-polygon to a GeoJSON. For that, we are going to use ArchGDAL. So let's do it. ArchGDAL, create a multi-polygon, geo interface, coordinates for our water coverage. Okay, it is now created. I'm going to create a new file over here. So open our, I guess, debug GeoJSON with write permissions, and then just write it on this file. The function that I'm going to use to convert to JSON, it's to GeoJSON, because GeoJSON is just a JSON file. Use it for geographical purposes. So water coverage AG. Okay. Did I write? Did I open first? No, I didn't. Need to run again. Okay, perfect. Now it did output something. Close the file. Perfect. And now I can open it over here. Debug GeoJSON. You can just copy and use this website geojson.io. Put your GeoJSON over here. And as you can see, perfect. We do have our calculated territorial waters over here. And actually, if we click here on OSM, we can actually compare with the real territorial waters over here. It does fit a lot, especially over here. Oh, this is a pretty good match. Of course, it doesn't fit completely because of the points, and I guess accuracy of the map doesn't have a lot of accuracy, but it's still enough for our purpose to show you guys how can you calculate the territorial waters of the country over here. It does look pretty good. Okay. Nice. There is also some islands that are not represented on our model, but yeah, it shows you how can you calculate this stuff. So maybe we can still use another function of our LibGEOS. So imagine that you got a boat on the water and you want to check if it is actually on the national waters or not. So let's check if, for example, if our boat is over here on this point. Okay, that is our coordinates here. Let's check if it is inside or not of our national waters. LibGEOS intersects. This is the same function that we used on tutorial 1. Water coverage with a LibGEOS point. Let me clean the plots over here on the left. So does it intersect? Yes, it does. If the point is in another position, let this one create a new one and outside of our territorial waters, and let's copy it again. So it's going to be pretty much the same thing. I'm just going to copy the same function and I'm going to change the values of the point. And in this case, it's outside of our water coverage that we have defined here. That is Madagascar national waters. Okay, guys, hope this tutorial was informative for you and hopefully it will help you on your GIS applications, or maybe you just want to take advantage of these geometry functions and use it for your own purpose.